Now, in module 2 of chapter 5, we shall learn a very interesting topic, that is called serret-frenet formulae for a space curve. Actually, Frenet has established this formula in his PhD thesis in 1847. Afterwards, Serret in different way has established this formula in 1851, but Frenet's formula also published in 1851. So, the formula is named as serret-frenet formulae for a space curve. So, in this module we will learn about these formulas. So, in module 2 we start with serret-frenet formulae. Let a curve, that is a space curve, be given by the equations x I equals to x I s. Now, here s, the arc length, is considered as a parameter. So, parameter s measures the arc distance along the curve. Now, we know that ds square equal to g I j dxi dxj from the fundamental metric. So, we can get g I j dxi ds dxj ds equals to 1. Therefore, dxi ds is a unit vector by the definition of unit vector, which was defined earlier in our chapter 3, that g I j a I a j equals to 1 implies that a I are the components of unit vector. So, here we are getting g I j dxi ds dxj ds equals to 1. Therefore, dxi ds is a unit vector. Now, if P be a given point with coordinate xi and Q is the neighboring point with coordinate xi plus dxi on the curve C corresponding to an increment ds in the arc, then the vector p q, where limit q tends to p dA by ds, is called the tangent vector, and which can be denoted by lambda I, where lambda I equals to dxi ds, that is the unit tangent vector to C. Hence, we can write g I j lambda I lambda j equals to 1. Now, taking the intrinsic derivative of equation 8 with respect to s, we have g I j lambda I del lambda j del s equal to 0. Actually, if we take the intrinsic derivative of equation number 8 and using the dummy index, that means we are changing the dummy index from I to j and j to I, we shall get twice of g I j lambda I del lambda j del s equal to 0, and which implies g I j lambda I del lambda j del s equal to 0. Now, from this equation we can have that either del lambda j del s vanishes, because lambda I are unit vectors. So, it cannot vanish, and obviously g I j will not vanish as we are in a space. So, del lambda j del s may vanish, or it is orthogonal to lambda I, because for orthogonal vectors we have this type of conditions. But del lambda j del s equal to 0 will imply that the curve is a particular type of curve, which we shall discuss later. So, we consider the next option, that means del lambda j del s is orthogonal to lambda I. Now, a vector which is orthogonal to the unit tangent vector at some point of a curve is called a principal normal vector of that curve at that point, and we denote this unit normal vector by mu j. That means, its components are denoted by mu j. So, by definition g I j lambda I mu j equals to 0, and del lambda j del s is codirectional with this mu j. Del lambda j del s have the same direction with mu j. So, we can write del lambda j del s equals to kappa mu j, where kappa is a constant and it is greater than 0, because equal to 0 will give us that del lambda j del s equal to 0, and we are not considering that case, but it may be 0. So, we have written the condition that kappa is greater than equal to 0, and kappa is a Greek word, and which gives us the magnitude of del lambda j del s, and this kappa is called the curvature of the curve at the given point. Actually, this curvature is measured on the plane of lambda I and mu I. That is why it is always greater than 0. Now, since mu j is a unit vector, we have this condition g I j mu I mu j equals to 1. Now, taking the intrinsic derivative with respect to s to the above equation, we get in a similar manner g I j mu I del mu j del s equals to 0. Now, again taking the intrinsic derivative of equation number 10, that means the condition where g I j lambda I mu j equals to 0, we get this one g I j del lambda I del s mu j plus g I j lambda I del mu j del s equal to 0. Now, using 11 in the above relations, we get kappa g I j mu I mu j plus g I j lambda I del mu j del s equal to 0. That means, we are replacing the value of del lambda I del s as kappa mu I. Now, g I j mu I mu j equals to 1. So, g I j lambda I del mu j del s equals to minus kappa, or we can write in this form also g I j lambda I del mu j del s plus kappa g I j lambda I lambda j equals to 0, since g I j lambda I lambda j is also equal to 1. If we take g I j lambda I common, we are getting g I j lambda I under the bracket del mu j del s plus kappa lambda j equals to 0, and this is equation number 14. From here we can see that del mu j del s plus kappa lambda j is an orthogonal vector to lambda I. Now, from 12 we have g I j mu I del mu j del s equal to 0, just we have deduced it, and this equation can be written in this form also: g I j mu I del mu j del s plus kappa g I j lambda j mu I equals to 0, because g I j lambda j mu I is itself 0. So, we can write this term as an addition, and if we take g I j mu I common, again we are getting del mu j del s plus kappa lambda j is a vector orthogonal to mu I. So, what we have observed that del mu j del s plus kappa lambda j is orthogonal to lambda I and also mu I. Hence, there exists a vector which is orthogonal to both lambda I and mu I, and we consider that vector whose components is gamma j. So, we can write gamma j equals to 1 by tau, it is a scalar multiple, del mu j by del s plus kappa lambda j, because this vector is codirectional with gamma j, where tau is chosen in such a manner so that gamma becomes a unit vector. Now, we know that lambda I are the components of unit tangent vector, mu I are the components of unit principal normal vector. So, we are choosing tau in such a way so that gamma j will form the components of a unit vector, and which is named as binormal vector. The sign of tau is not always positive, but we choose the sign of tau in such a way so that lambda, mu, gamma form a right handed system, and it is also called a moving triad. It moves along the curve. So, it is a moving triad, and this right handed system can be expressed in tensor form by the equation epsilon I j k lambda I mu j gamma k equals to 1, where this epsilon I j k and epsilon upper I j k are the permutation tensors defined in the following way. It is defined in the equation 18 that epsilon I j k equals to root over g e I j k, that is E system, and epsilon upper I j k equals to 1 by root g E upper I j k, and they are considered as a tensor of type 03 and 30 respectively. Just we have mentioned that this tensor epsilon I j k and epsilon upper I j k are called permutation tensors of E3. The vector gamma is called the binormal of C at the point P, and tau is called the torsion of C. So, we have obtained two new concepts, that is curvature, which is denoted by kappa, and the tau, which is the torsion of a curve. Now, from the expression given in 16, we have gamma I equals to epsilon I j k lambda j mu k, and that can be proved easily, and it is given afterwards, where lambda j equals to g I j lambda I and mu k are equal to g j k mu j are associated vectors of lambda I and mu j. Now, if we differentiate intrinsically with respect to S, we get this expression del gamma I del S equals to epsilon I j k del lambda j del S mu k plus epsilon I j k lambda j del mu k del S. Now, from equation number 11, we have this one, this expression, where the serret-frenet formula's first two equations have been applied. That means, del lambda j del S is written as kappa mu j and del mu k del S is written as tau gamma k minus kappa lambda k. Now, here the serret formula is used for the associated vectors. So, just simplifying this one, we are getting this expression, and now we are likely to find the expression given in the right hand side. We have epsilon I j k lambda j gamma k equals to minus mu I. So, this expression comes to del gamma I del S equals to minus tau mu I. Thus, we are getting three equations. One is del lambda I del S equals to kappa mu I, another one is del mu I del S equals to minus kappa lambda I plus tau gamma I, and another one is del gamma I del S equals to minus tau mu I. Now, we have here just shown that how the expressions are coming from the equation epsilon I j k lambda I mu j gamma k equals to 1. We are operating by epsilon I j k from both sides, and we are getting this expression, and if we just contract, we are getting this equation. Now, taking inner product with lambda I from both sides, we are getting this form lambda I and upper lambda I mu j gamma k equals to epsilon I j k lambda I. Now, as lambda I and lambda upper I equals to 1, because they are unit vectors. So, mu j gamma k equals to this one. And similarly, again taking product with mu j, we are getting mu j upper mu j gamma k equals to epsilon I j k lambda I mu j. So, gamma k is equal to epsilon I j k lambda I mu j. And similarly, we can get the expression in the same manner. We are getting the expression mu j gamma k equals to epsilon I j k lambda I, and that is lambda j mu j gamma k equals to epsilon I j k lambda I lambda j, and this is equal to 0, because in the left hand side as lambda j and mu j is multiplied. So, this is equal to 0. So, therefore, epsilon I j k lambda I lambda j equals to 0. Thus, the formulae del lambda I del s equals to kappa mu I, del mu I del s equals to tau gamma I minus kappa lambda I, and del gamma I del s equals to minus tau mu I are called serret-frenet formulae in space for a space curve in curvilinear coordinate system. Now, these formulas, just I have mentioned earlier that these formulas were formed independently by J. F. Frenet in 1847, but published in 1851, and Serret also published in separate way in 1851. So, its name is given as serret-frenet formulae. In matrix form, the serret-frenet formulae can be expressed as del del s lambda I mu I gamma I equals to 0 kappa 0 minus kappa 0 tau 0 minus tau 0 lambda I mu I gamma I. So, the matrix, that is transformation matrix, is a skew symmetric matrix. Thus, we can say that the serret-frenet formulae gives us the skewness of the curve. We can see from the figure here that a curve is given in a space and the unit tangent vector is given in this direction lambda I, and mu I is the principal normal direction, and gamma I is the unit binormal vector, and they are framing a orthogonal system which is a moving triad, and it can be also considered as a coordinate system, that is a moving coordinate system on a curve. So, in module 2 of chapter 5, we have learned about serret-frenet formulae for a space curve. Here we have seen that how intrinsic derivative of vectors and curvilinear coordinate system has been used. Thus, we end this module with this serret-frenet formulae.